So today and the next couple of days, I am going to be giving some lectures on what is called fixed parameter algorithms. But before I do that, I want to sort of set this context of the whole school, whatever we have been learning in the last week or two about what is the purpose of all that. I want to make sure that everybody is on the same page, right? So for that, I want to know from you what you understand by a problem is NP complete. So a problem I've written down could be, let's call it pi, but you can think of it as vertex cover, Hamiltonian cycle, independent set, whatever, some 10 problems you've learned. So what does it mean by it's NP complete? It's NP hard. It's NP hard and it belongs to NP. That is the definition. But what is the consequence? So what if a problem is NP complete? I mean, why is it important in the area of algorithms to know that some problem is NP complete? Okay. So hence, yes, so if the problem belongs to, if there is a polynomial time algorithm for this problem, then every problem in NP has a polynomial time algorithm. So what? Hence, P equal to NP. So it's unlikely to have a polynomial time algorithm. So we want to understand this, right? Because I'm trying to design efficient algorithm for a problem. That's the whole goal, right? Whole goal in algorithms for the whole course, that given this problem, we want to design some efficient algorithms for some notion of efficient. We'll come to that later. So let's say for now, polynomial time algorithms means that there is an efficient algorithm, right? So what she's pointing out is that if a problem is NP complete, it is unlikely to have a polynomial time algorithm. Okay, so let's write that down. So again, unless P equal to NP. So the consequence of this, I mean, there is a definition which you said, it is an NP and every NP hard, but the consequence is that unless, yes. Pi has no algorithm running in polynomial time. I mean, what does polynomial time mean? It's like n square, n cubed, whatever, if n is the input size. That gives an exact answer for all possible inputs. This is the consequence. This is what we understand. That's why we need to invest our time and energy on some other direction rather than coming up with an efficient algorithm, because it is unlikely unless P equal to NP, which most people don't believe. You don't expect a general purpose algorithm which will work for all inputs for this problem pi, and it will stop and give you an answer, exact answer for all possible inputs, and it will take polynomial in the input size. Okay. So if, for example, if you are talking about the vertex cover problem, that you don't expect unless P equal to NP, a polynomial time algorithm, it will take an arbitrary graph and an integer k, and it will tell you whether the graph has a vertex cover of size at most k or not all the time, right? Now, first of all, why should we care about polynomial time? What's the big deal about polynomial time? what is a non-polynomial function? Can you give me an example of a? Yeah, an example? 2 power n. Another example? N factorial. 2 power square root of n, right? 2 power log cubed n. These are all functions which are not polynomial. A polynomial is n power a constant, is what we know is polynomial. And why is polynomial time algorithm important? It's because, you know, in practice, one can actually do some calculations. Maybe if I'll bring it to some tutorial where you can come up with a table of as n increases, you know, if n is like 50 or 70 or 100, 2 power n algorithms will take hundreds of years to give the answer. Hundreds of years. Whereas an n cubed algorithm for n equal to 100 will answer in a few seconds. Okay? So maybe in some tutorial I will explain this in complete detail of, we will take an example of an n, take a problem, do our calculations and see how much a 2 power n algorithm will take and how much an n cubed algorithm will take on an input of size, let's say 100, and you will really see the difference. So somehow, because of this reason, polynomial time algorithms are supposed to be like feasible, something which can happen in practice in real time in a few minutes, few seconds. You will take your input of size 10,000, 100,000, and it will give you, if you have an n cubed algorithm, in a matter of minutes it will give you the answer. But if you have a 2 power n algorithm, even for n equal to 50 or 100, it might take some years. You and I will not live that long to see the answer to that question. Okay? So that's why we want to worry about polynomial time algorithms, because they work in practice. Okay. So now, given this situation, there is also one more reality, is that most of the problems which we want to solve are NP complete. Okay? So in a typical algorithms course, you learn about shortest path, spanning trees, sorting, searching. What else do you learn? Connectivity, BFS, DFS. That's the end of polynomial time algorithms. Okay? Everything else in the world is NP complete. It so happens most optimization problems in engineering, in VLSI, in operations research, combinatorial optimization, many domains, most problems they want to solve are NP complete. But then we have this story that if you really want to solve the problem in most generality, you have to live for a few hundred years to solve the problem for an input of size 100 or 200. Okay? If n increases even more, maybe you have to live 1,000 years or something to see the answer. Okay. So now how do we deal with it? What is the way out of it? Because we want to solve these problems. They are all practical problems, but they also turn out to be NP complete. So then we start relaxing one by one here. Okay? So maybe I don't want to solve the problem for every graph in the world. Maybe the graph I have has certain nice structure which I can exploit and design a polynomial time algorithm. Okay? This was the topic of Sunil Chandran's lectures of 3-4 lectures, where he said, okay, if the graph is triangulated, chordal, comparability graph, permutation graph, line graph, perfect graph, can we exploit these problems? In general are NP hard, so you don't expect an efficient algorithm. But if your input happens to be something special, maybe you can solve this in polynomial time. And this was the whole set of topics of Sunil Chandran's lectures. Okay? Now, you can relax this condition and say, hey, I may not want necessarily an exact optimum solution. I am willing to settle for something close to optimum if you can tell me in a few minutes rather than 200 years, right? Okay. So that takes us to the topic of approximation algorithms. So now, in the area of approximation algorithms, we take a really hard NP hard problem and say, okay, so there is one little difference I have to make clear, that NP completeness theory is all about decision problems, right? What are decision problems? Problems for which you have an yes or no answer. Now, what is there to approximate an yes or no answer? Right? There's nothing to approximate an yes and approximate a no. Well, you can talk about some randomized probabilistic algorithm. So, it may not give you an exact answer all the time, but it may give you a correct answer sometimes. That takes us to the world of randomized or probabilistic algorithms. But the more important question is, really, we really want to solve the optimization problem. Because of the historic reasons of Turing machine, the way language acceptance was defined, the whole notion of NP completeness was defined for the problem class of decision problems. But the point is, these are, if the decision problems are hard, optimization problems are going to be harder, right? So we are not restricting too much by focusing on decision problem, because we are talking about hardness. So when you talk about hardness, you say, hey, even a yes or no question is hard, so the optimization problem is going to be harder, because often you can use the yes or no questions multiple times to answer the optimization problem, right? Because if I want to know, is there a vertex, I want to find the minimum sized vertex cover. Okay, typically that is the problem we want to solve, because that's an optimization problem. But suppose I have an algorithm for the decision version, which will tell you, is there a vertex cover of size 25 or not? How can I use that to solve the optimization problem? Exactly. So in fact, no, it's the other direction. V will always be yes, right? So you start from, is there a vertex cover of size 1? That algorithm will tell you yes or no. If it said no, try 2. If it said no, try 3. And first time it said yes, you know that that is a minimum sized vertex cover. So often the decision problem questions can be used to solve the optimization problem, and that's why hardness and decision problems are okay. But when it comes to approximation, we are actually talking about the optimization problem. So the approximation algorithms are for optimization problems. So now here say I want to find the minimum vertex cover or the minimum traveling salesperson tour, but you tell me that minimum is very hard, I have to live for 1,000 years to see the answer. But what can you give me in a few minutes? Then we will give you something close to the optimum. Now, I don't even know the optimum. How can I believe you that this is close to the optimum, right? You give me some TSB tour whose total distance is 45. I have no idea how close it is to the optimum. So the real challenge in the area of approximation algorithms is the measure of the approximation ratio, how close to the optimum it is, and it is challenging because you don't even know the optimum. So you actually settle for the bound, some bound for optimum, compare it with the solution produced, and you argue that your vertex cover, maximal matching algorithm gives you a 2 approximation algorithm or something like that, right? So that relaxes this point about I don't want exact but something approximate, okay? Now, in this set of lectures which I am going to talk about, I am going to relax this point about not polynomial in input size, but little bit more, okay? Now, but I did tell you that exponential is a hard, algorithm will take several thousand years and so on and so forth. So now, what we will do is we will look at, in a sense, it is between these two areas, I would say, that we are going to look at some special input, but the special input is going to be parameterized in some sense, that my input graph has a certain parameter associated with it. I will explain what that means. Then if the parameter is small, I am happy to get a polynomial time algorithm. If the parameter is large, you may get an exponential algorithm. So there is a smoothness between small size parameters and large size parameters, and how can I capture my special input by certain parameter, and how can I capture my running time using this parameter would be the point of the discussion in this area of parameterized algorithms, okay? All right. Okay. So now let's get on to the famous vertex cover problem. Okay, so suppose I want to solve the minimum vertex cover problem, which in general is NP hard. But suppose I tell you that the graph you have is actually a tree. Okay? So it is a special instance in that sense. Can you think of or have you seen a polynomial time algorithm for this problem? So recall what a vertex cover problem is. It is a subset of vertices. Such that given any edge, at least one endpoint must be in this subset, right? So I am trying to find a minimum vertex cover, but I am told that the graph is actually not a general graph, but a tree. So how can I find the minimum vertex cover in a tree? What is the support vertex? Parent of a leaf. Okay. They have to be there. Okay. 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 So let me translate what he just said. So he's suggesting a following rule. So you have a tree. In fact, this rule is applicable for any graph, right? So first of all, let's do some pre-processing on the graph. Okay. So if the graph has isolated vertices, what can you do? Delete them. Delete them, right? Because we are trying to solve vertex cover problem. So we are trying to find minimum number of vertices to cover all edges. So if we are isolated vertices, they have no role to play in covering edges, delete them, right? So let's do delete isolated vertices. Okay, these rules will be very handy. So now the rule he is saying is the following. Suppose you have a degree 1 vertex. What does that mean? So you have vertex x, which is only one neighbor, and this, there may be other things going on here, but x has exactly one neighbor. Can you come up with some heuristic? You are trying to find a minimum vertex cover. So what can I do? Take y. Is everyone clear on this? I will point to somebody and ask. Okay? And if you are not clear, you raise your hand and ask me. Otherwise, I will point to somebody and ask. So if I have a vertex whose degree is 1, the suggestion is that take y into the solution. You are trying to find a minimum vertex cover. Take y. Why should I take y? Are you suggesting pick a high degree vertex? Okay. You are violently objecting. Why? Go ahead and say what it is. I mean, why can you just pick a high degree vertex? It seems like right. So right.
It doesn't cover no other edges.
Right.
So if I choose y, there is a probability that there is that.
Yeah. There is no harm at all. So you are giving an argument of why choose y, right? That look, this edge xy has to be covered. Has to be covered by somebody. Who can cover xy? Either x or y. In any vertex cover, optimum or not, in any vertex cover, x or y must be there to cover that edge. Okay. If x is there, just delete x and put y, and you will not be losing any generality, right? So, but I asked a different question and a side question. Why is it not a good idea to pick high degree vertices? It seems like a good idea, right? Because you are trying to cover edges. So why not pick a vertex? I mean, it seems like a natural thing. Any vertex which has the highest degree, include it in the solution. sometimes it won't be good, because this is a greedy algorithm, and greedy algorithm does not necessarily always give you a good solution. But let me put this as an exercise, because I mean this is something naturally, it's like first of all, the problem is NP complete. Okay, so you don't expect polynomial time algorithm by picking high degree vertices and give you optimum, because that seems like an easy polynomial time thing. Okay, but it's instructive to know why it doesn't work. So you have to. So this is why somebody pointed out about proof of correctness of algorithms are important, things like that, right? Because if you pick high degree vertices and you get a minimum vertex score, you need to prove that that's a correct thing, right? And I'll give you a simpler exercise. Disprove that, right? Disproving is easy, because you have to give an example and say, hey, here is a high degree vertices. I'm picking high degree vertices one at a time. And at the end, I got this solution, but actually the optimum is something else. Okay, so that's your exercise. On the side, show that picking high degree vertices don't necessarily give optimum. Sometimes it may. Okay, so this is a side remark, but now more or less several people seem convinced that if x is of degree 1 and y is its neighbor, with y as neighbor, pick y. This also requires a formal proof, and the way you prove it is that if you have an optimum solution without y, then it must contain x, because who is covered? Remove x and put y. That will also be a solution. You have not increased the cardinality, and that's also a vertex cover. So there is always a minimum vertex cover that contains y, so you pick y, right? So that is a reduction rule number 2. Okay. So now, once I pick something into the solution, I can delete that vertex, right? Because that vertex has done its job. It has covered all the edges. Now you're going to recursively go into the remaining graph and find the minimum vertex cover and add whatever you have picked to the solution, right? So that's the next step. So step 3 would be delete y, because y is into the solution, and continue. Okay. Now you can verify that all these steps are some easily linear time computable, because you're just trying to go into your adjacency matrix or adjacency list and finding a vertex of degree 1. Once you find it, you add it to your solution. You're deleting it from everywhere else. This is some linear n square time. And then continue this. Go back. If there are isolated vertices, remove them, and you keep doing it, right? What happens at the end? We are exhausted. We found the optimum solution. Our S, which you are trying to pick up, is the solution, the optimum solution, because every time you picked whatever is forced to be picked, and you picked, you can argue that vertex, there is a vertex cover that contains this, and then you're recursively computing this, and finally you finished. So you have a polynomial time algorithm to compute the minimum vertex cover. Where are we using the fact that the graph is a tree? That it will have a leaf, right? This rule the second rule applies only if you have a vertex of degree 1. If you don't have a vertex of degree 1, you have not progressed, you have not done anything. You remain in the graph and you're stuck, right? So, but thankfully we know, hopefully you learnt in the first lecture of this school, that every tree has at least 2 leaves. In fact, you can argue every tree on more than one vertices or more than one edge will have at least two leaves. So you can find a leaf, pick its neighbor, delete it. What you have is also a tree, so there will be a leaf. Find its neighbor, delete it, keep doing it. At the end of it, you have a polynomial time algorithm to find a vertex cover on a tree. Okay? So this is one of those examples of special instances where you can solve otherwise hard problem in polynomial time. So now let's see how I can generalize this. Now suppose I tell you I have an arbitrary graph, but not quite an arbitrary graph. Suppose I have G is a tree T plus some k vertices. Okay, so I give you this. So what does that mean? So there are these k vertices, or not even a tree. Let's even say a forest. Right, this whole thing, whatever we did, also works for a forest. Right, if I give you a forest and I want to find the minimum vertex cover, what will you do? How do I get the components? So you have a graph, let's say given in the form of an adjacency list or adjacency matrix, right? And I tell you it is a forest. So what does it do? How do you get the components of a graph? Hello? This is the first week lecture. DFS, BFS. Okay? These are exactly the reasons why you learned about all them, that you run your BFS or DFS and get the components of the graph first. And I tell you it's a forest, so each component is a tree. Apply the algorithm we just went through on each component and pick the set of vertices that cover all the edges. Together they will give you the minimum vertex cover for the whole forest. Okay? But now I tell you that the graph is not just a forest, but there are some k more vertices, which means it looks like this. So this is a forest. It's a collection of trees. But here is a set of k vertices, which I even give you. But these vertices are adjacent all over, right? So in a sense, it is like a special instance, parameterized by this k, right? But it's not a caudal graph or an interval graph kind of a graph, but it is just saying it is close to a tree. Okay? For tree, we can solve it in polynomial time, or close to a forest. Close to in the following sense that there are k vertices. If you delete them, the graph becomes a forest. I even give you the k vertices. Right? How do you find the k vertices is the other question. We will get to that later. For now, I say here is a set of k vertices. Okay? So graph looks more or less like a forest, but more or less only because it has some k more vertices. Now, can I design an efficient algorithm to find the minimum vertex cover in the graph? Okay? The problem is you may not have a leaf now, right? Why? Because this structure is a forest. The k vertices on the top may be connected to some of these leaf vertices, making them non-leaf anymore. So they are not a leaf anymore. So I can't apply the earlier rules. Let's assume there are no isolated vertices because you can get rid of them. But it's like all kinds of. First of all, yeah, okay. So how do we solve this problem? How does k play a role in the running time of the algorithm? These are the kind of questions we want to address. Okay. Okay, so I'll start with the hint and then you will be able to develop it. Okay, so we want to design an efficient algorithm for this problem. What is efficient? We will postpone that later. Okay, because I am not aiming for a polynomial in n and k kind of an algorithm. Why not? By the way. First of all, I cannot get a polynomial in n and k algorithm. Why not? Why? That's a correct answer, but what is the explanation? So what he's saying is, this is not really special. I mean, it is special subject to k, right? If k is large, then it is not really special. Okay? Because if, what he is saying is if you solve this problem, minimum vertex cover problem on this, you will be able to solve it for any general graph. Why? How do you reduce a general graph to this? Wait, I am deleting vertices, remember, okay? Yeah. So, I am just saying there is some subset of vertices. If I delete, the graph becomes a forest. Can you find such a subset in any graph? But you are deleting vertices, remember. Okay, so which vertex you would delete? So, cut vertex, it's actually a completely trivial question. So, don't think very hard. I am asking, given a graph, because k I am not fixing you, arbitrary k, whatever k. Minimal separator, oh my god, I don't know whether everybody knows minimal separator. So, I just said it's a trivial question, right? So, I'm here, let me repeat the question. I want everybody to participate. Given a graph, can you find some subset of vertices? When you delete, the graph becomes a forest. There you go. He says, delete everything. Keep maybe one vertex. Maybe keep two vertices, right? Delete n minus, where do we need minimal separator? Right? Delete n minus 2 vertices. What is left? It may be 2 isolated vertices, or maybe there is an edge. It's a forest. There is no cycle. Right? So, every graph has a certain subset. The only problem is k is very large here. So, you don't expect a polynomial in k and n kind of an algorithm. In fact, this is what we have shown is actually the problem is NP complete. That's exactly what we did. Right? Given an arbitrary graph and arbitrary vertex cover question, I can reduce it to a graph which has, some n minus 2 vertices whose deletion results in a forest. And if you can solve this in polynomial time, you can solve the general graph. So you don't expect polynomial time algorithm. But so k has to play a role, and there will be some exponential, and we'll see how to do it. Okay, good. Okay, so let's come back to the picture again. There are some k vertices here, and I have a bunch of trees. So this is my whole graph looks like this. Okay, and I want to design a minimum vertex cover for this problem. So let me start with the following idea. Right. So you have, suppose the solution S. I don't know. I am asking for a minimum vertex cover. Let's say that solution subset of vertices is S. It's called this M, right? M is this modulator, subset of k vertices whose removal makes the forest. Suppose S intersects M in some set Y. Okay? So I don't know this Y. I am looking for a solution minimum vertex cover, and let's say the minimum vertex cover intersects this modulator in some subset Y. Okay? I don't know this Y because I don't know S. Okay? But we will run through all possibilities. But once I fix, and let's say I decide somehow that S intersects exactly at Y, intersects M, I think the rest of the problem is easy now. Let's see why. Okay? I'm trying to build a vertex cover, minimum vertex cover. Somehow I made a guess and said it intersects M in this set Y. That means these vertices are not in my solution. I'm building up, right? Because I've decided that the intersection of my solution with M is only this set Y. The remaining M minus Y is not in my solution. Okay? If it doesn't work, I'm going to try a different possible set Y and keep trying all possibilities. So what can you observe from this? Can we? There is no edge in this M minus Y induced subgraph, right? you cannot have an edge here. Because if there is an edge here, who is going to cover this? Because these vertices cannot cover that edge. If I find some edge here, I will say y is a wrong guess. I am going to try a different subset y. Okay. So there are no edges here. What else can you conclude? So remember, there are all possible edges across, right? There is nothing here, but there are edges like this. Who will cover those edges? Who? The vertices at the other endpoints in the forest, right? Basically, for every vertex in M minus y, then the neighborhood of M minus y intersection V minus M must be in S. Right? This notation you understand, right? Look at the M minus y vertices, which are, this is M, this is y. If you look at the remaining vertices, their neighbors, all of them outside, must be in my solution I am building, because they are the only ones who can cover these kind of edges. Because I have decided I am not going to pick these vertices. Okay? So now I can delete these guys. I can delete y, because y I have decided to include in my solution, put it in my pocket. Take M minus y, look at their neighbors, include them into my solution, delete them. What is left? A forest in which I can find a minimum vertex cover in polynomial time. So apply that and you get the minimum vertex cover for, because the forest, there will be different all edges across in the trees and so on, you need to cover them, but we know how to find the minimum vertex cover in the polynomial time. So collect all of this together, you get a vertex cover that contains y. But maybe final vertex cover may or may not contain y. So try all possible subsets of y. Try all possible subsets y of M and pick the one which is the smallest. And I claim that that is the minimum vertex cover. Okay? So remaining vertices form a forest. So let me describe the entire algorithm now. So for every y contained in M, let S be a minimum vertex cover of the induced graph on y minus M minus neighborhood of M minus y intersection V minus M. Lot of notation here. I will come back and explain all of it again. We went through it. And S prime equal to S union y union neighborhood of M minus y intersection V minus M. And pick the S prime of smallest size. Okay, so in a forest we know how to solve in polynomial time, and I am trying to extend it to the class of graphs which have some k more vertices whose deletion results in a forest. And what am I doing? The algorithm simply says run over all subsets y of the modulator. So I first fix one subset y of the modulator, and I am saying that y is going to be in the solution I am trying to build. Then I have to take y. Then I have to take all the neighbors of M minus y. m minus y in this set, the remaining set, add them into the solution, delete them all. In the remaining graph, it's a forest, find the minimum vertex cover, add it. Now you have these 3 different sets, together you get a vertex cover of the whole graph, right? Run it over all possible subsets y and pick the smallest one, and that is the minimum vertex cover. Okay, one can prove that this actually produces a minimum vertex cover. Now comes the important part of, let's say we sort of more or less proved that algorithm is correct, because essentially we are doing whatever is necessary. Once you fix y, whatever else we are doing is something necessary, because you know you are not allowed to pick m minus y, so you have to pick the neighbors of m minus y. Once you pick them, you delete them, what is remaining is a forest, and find a minimum vertex cover, collect all of this. So this gives you a vertex cover containing y. Running over all possible y gives you a minimum vertex cover. Okay? But what is the next? Analysis. Now we want to understand how much time the algorithm took. Okay? Let's see how much time. So I've written. So any questions on the algorithm? We had a very simple algorithm for a tree, which simply says pick the neighbors of a degree 1 vertex. We keep applying it, which we said applies for a forest as well. Now I said, okay, let's say you have a forest plus some k more vertices. Then once you make a guess on the intersection of my solution with the modulator, life becomes easier afterwards, and run over all possible guesses. So how much time does this take? Well, how much time does it take to find the minimum vertex cover of the remaining forest? Some polynomial time. Okay, we will not be very careful and say whether it's n square, n cubed. For now, let's say it's polynomial time. So computing s is some polynomial time. So y is made my guess, and then looking at the neighbors of m minus y is, again you can go to your adjacency matrix and pick them all. So all of this is for one particular y, it is a polynomial time algorithm. How many possible y's are there? 2 power k y, number of subsets of m, and since m is of size k, it's 2 power k subsets. So overall running time of this algorithm is order 2 power k times some polynomial in n, where this c is constant independent of k. And so here is a problem which comes with the parameter k, and I have an algorithm of this running time. So let me introduce a notation here which I will use. Again, it's there in your problem sheet, which often I'm going to ignore this polynomial term. So I'm going to call it O star 2 power k, which means that it's O 2 power k times some polynomial in n. Okay. Yeah. Yeah. What is S? Okay. So what am I doing? V minus, you are right. Good question. Thank you. So it's take the V minus neighborhood of m minus y intersection v minus m, and I also delete m. Right? From the whole graph, I delete m because I have already picked y and the neighborhood of m minus y into my solution. I delete them as well. So from V, I am deleting m, and I am also deleting neighborhood of m minus y. And what I have is a forest. In that, I am trying to find a minimum vertex cover and add it to my y and add to the neighborhood. And so the 2 power k comes because I am trying all possible subsets of the modulator. And the modulator size, I assumed it to be k. Okay. So here really, I'm exploiting the fact that this k is. So clearly, this algorithm looks like an exponential algorithm. It is an exponential algorithm. But if k is small, right? If k is a constant, it's a polynomial time algorithm. What happens if k is like log n? Still polynomial. Why? 2 power log n is n. Everybody clear? This is an important thing which is useful to know. You may miss it. 2 power log n is actually n, because that is actually the definition of log. Right? What is the definition of log? How many powers of 2 is sitting in n? That's what definition of a log is. So 2 power log n is n. So what this tells you that, so what if k is 3 log n? It won't be n cubed. It's still polynomial, right? So this algorithm has a dependence on k, and we argued that you have to, because I mean it has to have an exponential depend on k, because otherwise you can solve the general vertex cover in polynomial time. But this, we have sort of separated the parameter somehow, right? There is a parameter I introduced, and we separated it and said you have an algorithm of this running time 2 power k times n square n cubed. So up to k being constant or order log n, this gives you a polynomial time algorithm. So now we are enlarging our input instance from just a forest to something forest plus some log n many more vertices. Even then we can solve vertex cover in polynomial time. Okay. So this is the notion of fixed parameter tractable. So this problem is said to be fixed parameter tractable, where the parameter is k, which is how far it is from a forest in this definition. Okay. So let's do one more example. So the thing I want to mention is that your input now in this world of fixed parameter algorithms, there is some x, which is a string or a graph or something, plus there is some parameter now we are going to associate with it. In the example we saw, the parameter was how far the graph was to a forest. But the parameter could be anything. Anything which makes sense, which is more interesting, which comes up in practice. It could be the degree of a maximum degree of a graph. It's how close to a tree the graph is. Whatever you can come up with. Number of vertices with a degree more than n by 2. You make a definition of a parameter and you can study it. So this provides a framework to analyze and design algorithms in some sort of a multi-dimensional way. Right? Earlier, n was the input size, and your algorithms were designed based on this n and polynomial 2 power n, n square, whatever. Now I am throwing in an additional secondary parameter. Now we will design and analyze algorithms both as a function of n and k. Okay? And a problem is called fixed parameter tractable. A parameterized problem. There is an abbreviation called FPT. If you have an algorithm whose running time is some function of k times, so this x is like n, we write, right? Where this c is independent of k. i.e., you have an O star f of k algorithm. Okay. So we'll see one more example on a parameterized problem and a fixed parameter tractable algorithm. And you can see that it sort of naturally comes between, at the one extreme you have a very efficient algorithm for a forest. At the other extreme you have an exponential algorithm on general graphs. This nicely smoothens the set of graphs in between using some parameter, and then you can distinguish your running time algorithm based on the parameter and the input size. Okay. So, let me define a cluster graph. Okay, did you come across this term in the school? Cluster graph. Okay. A graph is a cluster graph. It's very simple. If every connected component is a clique. Okay. Okay. So, can you check whether a given graph is a cluster graph? By an algorithm, what sort of an algorithm we'll need? And then that's it, right? It's very easy, right? There's nothing hard. It's really, I want everybody to understand this. If you don't, please ask others, ask in the tutorial and understand it, because this is absolutely trivial thing. And if you don't understand or if you don't care, you might as well leave the school. No point in wasting your time for the rest of the school, right? Because I want people to be engaged in the school. At least simple things. I can understand hard things you may not be able to follow, but get into the habit of just learning something, at least the initial things, right? So, I just defined a class of graphs. A cluster graph is it's a graph where every connected component is a clique. A clique itself, if the whole graph is a complete graph, it's a cluster graph. And how do I check whether a given graph is a cluster graph? Well, find all the connected components. How do you find all the connected components? BFS, DFS, first week lectures, right? You will get all the connected components. Go to connected components and check whether every edge is there in between every pair of vertices there. So that's all there is, right? So it's a trivial polynomial time algorithm. So now, but the question I am interested in, you are given a graph G and an integer K. The graph may not be a cluster graph. Graph is an arbitrary graph. What we want is, does there exist a subset of the vertex set V? So, this is V comma E, whose size is at most K, such that G minus S is a cluster graph. Right. So, I may have an arbitrary graph like this, and I ask, can you find a subset of two vertices whose deletion will make it a cluster graph? Can you do that in this graph? Can you delete two vertices and make it a cluster graph? No. Okay, on the other hand, you can find three vertices whose deletion makes it a cluster graph. So, this is the problem. I want an algorithm for this. I give you a graph, arbitrary graph, in the form of an adjacency matrix list, doesn't matter for our purpose. And I say, I give you a parameter k. Can you delete k vertices? The graph becomes cluster graph. Okay. But what we all agreed and checked is that given a graph, is it a cluster graph is easy. You can do it in polynomial time. Okay. So now can you give some sort of a brute force algorithm for this problem? That is even more clever. I want a brute force algorithm. Because the brute force algorithm proof will be very simple. And yeah, see, that's a brute force algorithm. It's very easy to give a proof of correctness, right? When you say high degree, low degree, I need to worry about why should it always give you a correct answer, and I need to prove it properly. So his algorithm is take a k-size subset, delete it, look at the remaining graph. We know in polynomial time how to check whether it's a cluster graph, check it. If not, try another k-size subset, try all possible k-size subsets, and if you succeed for any one of them, the answer is yes, otherwise it's no. How much time will this algorithm take? Yes? So let's say we can check, we can delete vertices and check everything in some n square time. Then how much time will the overall algorithm take? Yeah. N power k times some n square, right? So this algorithm, try all, basically I'm going to write this as try all less than or equal to k sized subsets to delete and check. And this algorithm is like n power k plus 2 or something, because n power k is the number of guesses I am trying, and for each guess the deletion and checking whether it's a cluster graph, let's say it takes n square time. So overall it's n power k plus 2 time. Okay, k is in the exponent, again which you expect because one can show that this is also an NP complete problem. But this is not the kind of running time I looked for, right? Because what did I mean by a fixed parameter tractable kind of thing? I want f of k times n power c, where c is independent of k. I don't like k to sit on top of n. Okay? I mean, this is the kind of algorithm I'm looking for. Like the 2 power k n square algorithm was nice. For the tree plus k vertices vertex cover, we had 2 power k n square, where k was not sitting on top of n. The function of n was a pure function of n square n cubed kind of thing, and there was a pure function of k which is separated. Any problem with such an algorithm is what I called as a fixed parameter tractable problem. Okay? But this algorithm which we just came up with is not of the type, but we will design one. Is that clear? That this is not the kind of running time I want? Yes? What are we aiming for? I want an algorithm. I mean, if I ask the question, is it fixed parameter tractable? Means, is there an algorithm whose running time is some n cubed or something like that? This constant is independent of k. So we are trying to separate the function of k and pure polynomial linear, and this is very useful when k is reasonably small. Regardless of n, you will have a reasonably practical algorithm. Okay? I am not saying this algorithm's running time is this. I am saying this is not the type I want, and now let's design an algorithm of this type. It should be independent of n. Yes. So it could be 2 power k, k power k, k square. It certainly can't be polynomial in k, because again we are dealing with NP hard problems, so it will be exponent. So it will be like a 2 power k or 3 power k. In particular, I don't want k to sit on top of n, because then the running time has an effect. If n increases and k increases, you have a problem. Whereas if I have something like this, it's only the k, as long as k is reasonable, regardless of n, I will have a reasonably practical algorithm. Okay? Now we are going to design such an algorithm for this problem. We will do that. And the starting point of the algorithm is the following different characterization of a cluster graph. Okay? So G is a cluster graph. if and only if G has no induced path on 3 vertices. So, for example, I do not like this kind of a thing, that x y is an edge, y z an edge, but x z is not an edge. Okay, so, path on 3 vertices is induced, meaning there is nothing else, no other edge is there. Okay. First, is the statement clear? I am giving you another equivalent definition of a cluster graph. One definition we saw that is every connected component is a clique. Now, I am saying here is another equivalent characterization. You go to your graph and see whether you have some structure which I call P3, induced path on 3 vertices, that you have x y is an edge, y z is an edge, but x z is not an edge. If you have such a structure, I claim that it is not a cluster graph. That direction is actually easy to see. Think about it. Can we have such a structure in a cluster graph? Because where would you fit these 3 vertices? Every connected component is a clique, right? So, x, y, z should sit in one connected component, but it is a clique. So, how can x, z edge be missing? So, this is one direction, that if you have such a structure, it cannot be a cluster graph. I am now saying that the converse is also true, that if you have a graph which does not have any of these structures, then every connected component is a clique. Okay. I am not going to give a proof of this, it is in the problem sheet, we will discuss it in the tutorial or think about it, that proof of this. Now, let us see how I can use this to design an algorithm of the type I want. Okay. So, I am going to call it this FPT algorithm. Remember, FPT means fixed parameter tractable, which means it is of the type some f of k times polynomial n. Okay. And the problem again, you are given an arbitrary graph and I am asking, can you delete k vertices to make it a cluster graph? Okay. So, the algorithm, step 1. Check if G is a cluster graph. Right. So, you are given some G and a k, and k is greater than or equal to 0. Right. You know how to find whether a graph is a cluster graph. Suppose I run it and find it, and suppose it happens to be a cluster graph, what can you say? If yes, then yeah, the question is, can you delete k vertices? Yeah, its answer is yes, you can delete k vertices. You can delete 0 vertices to get, because G itself is a cluster graph. K is greater than or equal to 0. So, I say return yes. Right? G itself is a cluster graph, so I do not even need to delete anything. Now, you want me to delete at most k vertices, at most k, remember. Right? Yeah, so yes, k is at least 0. So, yes, you do not have to delete anything, it is a cluster graph. Else, we know by the characterization that you will find this P3. Okay, this is also in the problem sheet, which in a linear time you will test whether a graph is cluster graph, and if it is not, it will actually find a P3 and say here, this is why it is not a cluster graph. Okay. So, you will find a P3. Okay. Now, what can you say? Suppose you find a P3 x, y, z, and I am trying to find a deletion set. So, what can you conclude? Yes? Delete? Delete y. I do not know how the rest of the graph is, remember, right? This is once a structure. There may be lots of other things. So, You never know, there may be lots of P3s like this. In this case, deleting y may not be a good idea. What is a better idea? In this case, deleting z. So you don't know. If I look at only these three things, what can you definitely conclude? One of the three vertices must be in the solution, right? Safe. Let's make simple observations which are easy to prove, right? That's the whole idea. You try and make too clever things, then it's very difficult to prove. So all I'm trying to now say is, hey, x or y or z must be in any solution, because you can't let this P3 survive. You won't get a cluster graph. You need to kill this P3. The only way to kill this P3 is to delete x or delete y, delete z. I don't know which one is the better thing because I don't have a full structure of the graph. So I'm going to try one by one, try all the three possibilities. Okay? What does try one by one means? Delete x and recursively look for a deletion set of size k minus 1 because I have deleted 1. So now I delete x, in the remaining graph look for a deletion set of size k minus 1. If you succeed, great. Take that x and this and say, here is the solution. If you did not succeed, I'm going to delete y and try the same thing. If you did not succeed, try z and delete. And none of them succeeds, then you know there is no solution because, hey, one of them has to be deleted. So that's the algorithm, right? Now comes the analysis part, right? That's a key thing. So I'm going to say, this is the word which we will use, branch by deleting x or y or z. Okay? So I'll draw a picture here. So you can think of some sort of a recursion tree. I start with g and k, right? I have my graph g and I am looking for a deletion set of size k, and either you did not find a P3, the graph itself is a cluster graph, then you will stop and say yes, the answer is done, or you will find a P3. Let's say you find a P3 x, y, z, then you g minus x and look for a k minus 1 size solution, or g minus y and look for a k minus 1 size solution. It's a recursive algorithm. G minus z and look for a k minus 1 solution. Okay? It's a recursive algorithm. So you can analyze recursive algorithms multiple different ways, write a recurrence relation, or just keep branching it out and unravel the recursion tree, and we can see. So what happens in the next step here, let's say, in g minus x, I'll see whether it's a cluster graph. If it is, I'll stop. If not, I'll find a P3, and I have a three-way branching here. Same thing happens here. How long does this go? What would be the depth? K. Why? Because k is dropping at every step. I start with gk, k minus 1, k minus 2. Eventually, I'll reach a graph and say, is there a zero deletion set to get a cluster graph? What do we do there? Check whether it's a cluster graph. You don't need to do any more branching there. If it is a cluster graph, you will say yes, otherwise you will say no in that branch. Because you have to delete, you have no budget to delete. So you have to check whether G is a cluster graph or not. So at the leaf levels, at the step of k, you will stop here and check whether it's a cluster graph or not. And if it's not, you will say no. So now, some branches will say no, some branches will say yes, and wherever if you have an S here, you pick all the vertices you collected, and that will give you a k-sized cluster deletion set. Otherwise, the answer is no. And how much time does this whole thing take? 3 power k, because 3 power k plus 1 or something like that, because it's a three-way branching tree to a depth of k. So it will be 3 nodes here, 3 square, 9 nodes here, and 3 power k. So overall, it's 1 plus 3 plus 3 power. So it's order 3 power k number of nodes. And in each of them, how much effort are we putting in? What are we doing? We are finding a P3, we are deleting some vertex, all that is some n or n square time. So overall running time would be order 3 power k times n square, or more simply it's O star 3 power k, okay, which is better than the n power k plus 2 algorithm we had, and this is of the type, nice type which we wanted, some f of k times polynomial n, so we could split the k and the n. Okay. Good. So, to summarize, I have just told you a notion of fixed parameter tractable algorithms. So, the input always comes with some input and a parameter. The parameter can be anything which is more interesting. It could be the, so in this example, in the cluster deletion set, I have chosen the parameter as the solution size. Okay. If you look at the minimum deletion set, I am looking at the solution size as the parameter. In the other example where we looked at tree forest plus k vertices, where we were trying to find minimum vertex cover, the parameter was how far the graph, the input graph was to a forest. So, we can choose parameter in whatever way you like. Most often we will choose k as a solution size, and an algorithm or is called a fixed parameter tractable means that we want an algorithm. We are looking at hard problems, so there will be something in the exponent, but we are trying to separate them, an f of k and a polynomial in n. The polynomial n is a pure polynomial in n independent of k, and we are trying to design what problems have this kind of an algorithm. Okay. There is also a notion of hardness theory here. We can show that there are certain problems which cannot be solved in this kind of a running time. We will see that, like analogous to NP complete reductions, we will see a notion of some completeness and some reductions, and we will see more algorithmic techniques to design such kind of an algorithms. Okay. I will stop here, and the motivation is clear, because as I said, most problems are NP hard, and we are trying to parameterize something and do some sort of a multivariate analysis of the algorithm. Okay. So, I have a problem sheet which is already passed out on this idea of branching. Okay. So, the key idea of branching is you find some structure which you have to kill. In the case of cluster graph, it was a P3 which we were trying to kill, and there are 3 ways of killing it here. Now, in other cases, you may find some larger structure where you have to do something, you have to delete this or add something or kind of thing, and it is like your backtracking algorithm. Try all possibilities, but the possibilities are measured and bounded by this function of k is what we are trying to do. So, find some small structure to kill, and we will branch on all possibilities, the ways in which you can kill them, bound the depth of this tree, and that gives you something like a c power k times polynomial.